Hello everyone, my name is Jianmin Guo. I'm a PhD candidate from Tsinghua University. I will introduce our TSE work for you. It's RNN test towards adversarial testing for recurrent neural network systems. As we all know, deep learning is widely used in safety-critical systems such as self-driving cars, cancer diagnosis, and malware detection. So it's essential to ensure the correctness of deep learning systems. However, deep learning can be easily fooled. In these pictures, just apply some invisible perturbations to the original pictures, the neural network will make wrong predictions. It may cause huge damage if applied to the real world. In a Tesla auto-driving case, a truck is misclassified as sky and caused severe traffic accident. Therefore, deep learning testing is quite challenging. As for existing deep learning testing methods, they mainly focus on CNNs and image classification tasks. However, there is a huge gap between CNNs and RNNs in model structures and tasks. Here is a typical DNN, including two major types, CNN and RNN. They have different model structures. CNN is widely used in image classification, auto-driving, playing Go. RNN is mainly used in natural language processing, speech recognitions. Due to the huge gap, testing methods and coverage criteria for CNNs are hard to fit for RNNs. Here gives a brief introduction for convolutional neural network. It's a feed-forward structure, that is, the outputs of previous layer will be fed into the next layer. CNN introduces convolutional layers, pooling layers, which are good at image processing. In CNN testing works, feature map is treated as a neuron and employ neural-based coverage metrics to test related models. Recurrent neural network is not a feed-forward structure. RNN models iteratively make predictions given inputs. RNN includes three key components: hidden state, self state, and gates. Self states and gates make RNN models good at learning context and thus widely used in natural language processing tasks. This picture illustrates the basic structure of RNN, where a cell iteratively makes predictions Y-hat based on inputs X and hidden states at H. When it is unfolded, the input sequence X is fed to the RNN cell as a series of time steps. X could be a sentence and XT is the Tth word. Moreover, each prediction YT-hat could be the predicted word right after XT, based on the received sequence. For different RNN models, they are of this similar structure, while only LSTM models have cell states. The main differences of RNN model structures lie in the cell. LSTM and GIU introduce multiple gates for keeping context information and become mainstream RNN models. Then want to take into consideration when designing testing methods for RNN systems. First, neuron-based coverage metrics do not generalize well for RNN models. First, such as RNN commonly have 1 to 3 layers and dozens of cells when unfolded. CNNs usually have dozens of layers and hundreds of neurons. We found that neuron coverage guidance fails to produce adversarial inputs over a small RNN models we tested. Accordingly, we defined two novel state coverage metrics for RNN models. Secondly, RNN models compose of hidden states, self states, and gates as key components. We designed state inconsistency guided search to search for adversarial inputs for RNN models. Third, many RNN testing works neglect sequence-to-sequence domains. There is no rule to recognize sequence outputs without class labels and adversarial inputs. We propose RNN tests to systematically test sequence-to-sequence tasks, which is not limited to classification tasks. Finally, lots of sequence-to-sequence tasks receive discrete inputs like text. We apply different domain constraints according to input types, such as for tasks with text inputs, we will scale the perturbation to search for adversarial inputs in the discrete embedding space. Now show the workflow of RNN test. Given the tested model, RNN test will focus on the RNN structures without other components for specific tasks. For original test input X, the first step is to extract the hidden states and cell states of each RNN cell. These states are then used for the state inconsistency guided search. This is a joint optimization. The first part intentionally violates inner dependencies of RNN states to lead the model to exhibit unusual behaviors. The second part, cover guidance, tries to cover more states to exercise more decision logics. In this way, RNN test could search for adversarial inputs in a scalable way. Then the joint optimization problem will be solved in a gradient-based way and acquire minute perturbations. When got the perturbations, adversarial inputs are easy to obtain from models with continuous inputs like speech by applying perturbations directly to original inputs. For models with discrete inputs like NLP tasks, the perturbation applied to the test input will probably not lead to a legal input. Here we adopt the nearest one adversarial input after searching along the perturbations. Finally, these adversarial inputs will be assessed with model performance and coverage to help subsequent testing. The first part, adversarial search, tries to maximize the state inconsistency to induce errors. Here are the computations of these cells. Since sigmoid and tangent functions are monotonically increasing, there are positive dependencies between hidden state and the hidden state of the previous cell in the same layer, as well as hidden state and the cell state of the current cell. The statistics over test models demonstrate this common case. So, adversarial research guidance intentionally violates these dependencies to trigger errors in RNN models. The second part, coverage guidance, tries to boost state coverage to execute more decision logics of RNN models. It selects hidden states or cell states to cover and then increase the coverage. Here, hidden state coverage and cell state coverage are two novel metrics introduced in our work. These two pictures illustrate the hidden state and cell state. For hidden state, each represents the output of each RNN cell. It's a vector containing hundreds or thousands of units. Here, each rectangle represents each unit. A darker color means a higher value. When to predict the next word following A, these hidden state units will be mapped to a list of candidates. If a hidden state unit is the maximum, its mapped candidate will probably be the prediction result. So we define hidden state coverage to measure each hidden state unit, whether it's used for prediction. For cell state, C is the output of each LSTM cell. It's also a vector of cell state units. A rectangle is also a cell state unit and darker color for higher value. When predicts the predicate after day, it will receive context from previous steps and keep the key semantics and remove those invalid, and then to compute predictions. So we define self-state coverage to measure each self-state unit, whether it is used for context preserving in different degrees. For evaluation, we select 4 RNN models, including 3 sequence-to-sequence models and 1 classification model. PTB language model and spell checker model are natural language processing models. Deep speech ASR model is a speech recognition model. Their underlying model is of LSTM structure. MINIS GRU model is an image classification model of GRU structure. Then MINIS LSTM model is for comparison to other RNN testing works. We select these diverse applications to evaluate the effectiveness of RNN tests. This table presents the effectiveness of our RNN test compared with FGSM and DLFuzz. We mainly select these 2 works because our earlier work is among the first attempts for RNN testing, and we try to prove the necessity to design testing methods especially for RNN models. Over the testing models, we can see that RNN test outperforms FGSM and DLFuzz, declining the model performance more sharply with higher success rate. Here, RNN test with hidden state coverage is for common RNN models. RNN test with self-state coverage, especially for LSTM models. As for other RNN testing works, RNN test achieved higher adversarial rate than test RNN out of the test cases obtained. And for Deep Stellar, RNN test achieved 53 to 58% more perplexity with higher generation rate over PTB language model. Then we evaluate the effectiveness of coverage guidance. First, we found that coverage guidance could produce different perturbations with other methods. Here we present T-SNE transformations of perturbations of diverse optimization objectives for the same input, where search is adversarial search, coverage is coverage guidance, and joint is joint optimization. The diamond distribution represents various perturbations and thus different adversarial inputs. Then, according to our experimental results, state coverage metrics as guidance could obtain adversarial inputs superior to neuron coverage guidance, whether independently or jointed with adversarial search. Here we can see that neuron coverage guidance fails to obtain any adversarial inputs on PTB language model. Furthermore, both FGSM and DLFuzz with state coverage guidance gain higher effectiveness than themselves and those jointed with neuron coverage guidance. As for the correlations of coverage values and testing effectiveness, weak positive or negative correlations are found between the model performance and the values of coverage metrics shown in these figures. Therefore, we suggest that more efforts are needed for adversarial testing with the coverage guidance, but not just to improve the coverage value. Then, here gives sample adversarial inputs over the testing models. For PTB language model, RNN test mutates one word which is randomly selected to obtain adversarial inputs. Results show that adversarial inputs of RNN test result in the model sampling words farther from semantics and generating text of higher perplexity. For spell checker model, RNN test mutates one character randomly selected to obtain adversarial inputs. Adversarial inputs of this model could result in the corrected mistakes in the original inputs appear again in the predictions of the adversarial inputs. For deep speech ASR model, here the adversarial input of RNN test. The original input of blue thin line is overlapped with the adversarial input of yellow thin line. Each waveform is 500 samples long and was chosen randomly from the inputs. The original input prediction is the shop is closed on Mondays, but the prediction result of the adversarial input is wrong. Such adversarial inputs may harm the security requirements. For ministerial model, here are samples of adversarial inputs for the same original input on ministerial model. The original image is classified correctly as 9, but 3 adversarial images of different methods are classified as 4. Finally, we incorporated adversarial inputs to the training set of PTB language model. After 12 epochs, the training performance reduces a little, but the valid performance improves. Besides, the text perplexity after the training, it declined by 12% compared to the original perplexity. Thus, these adversarial inputs improve the model. Now we conclude. RNN test is the first step towards systematically testing sequence-to-sequence domains for RNN models. In this paper, we propose a novel search algorithm by maximizing the inconsistency of RNN states to produce adversarial inputs, which is fit for most RNN systems. We also designed 2-state coverage metrics and demonstrate that the contributions of cover guidance to adversarial testing. Finally, RNN test exhibits impressive effects with other works. Our future research will be more powerful testing tools for specific tasks, such as targeted audio adversarial attacks. Moreover, transformer models become more and more popular in deep learning. Effective testing methods over transformer models are in need now. That's all. Thank you very much. You can check the paper for more results, and the source code is released now. Welcome for more discussions. Thank you.